So we're looking at the Northwest Trials 2022 Acids and Bases question, which was a bit of a tricky question. It dealt with an acid and a base that was added together, and you had to calculate the pH of the final solution when the two were added together. So let's start from the beginning. So you have two beakers, beaker A, which has your acid in it, okay, which is carbonic acid, and beaker B, which has a base in it, which is sodium hydroxide. Okay, as we go, if I feel it's necessary just to remind you of some things, I'm just going to make a note of it. So first thing, they've given you the volume and the concentration of the acid, but it is carbonic acid, and carbonic acid is actually a weak acid, which is important. It's very, very important that we know our list of strong and weak acids and bases when we start these questions, because it has an effect on how you answer the question. So maybe we should start by just talking about strong acids. Which are your strong acids? Okay, and why it's important. Your strong acids are HCl, sulfuric acid, and nitric acid. Okay, so that's hydrochloric acid, sulfuric acid, and nitric acid are your strong acids. Okay, at school, those are the ones we deal with. All the others, they give you like carbonic acid and acetic acid and oxalic acid. Those are all weak acids. Okay, then when it comes to bases, our strong bases are your group 1 and 2 hydroxides. Those are your strong bases. And the other bases, like ammonia, for example, is a weak base because it's not a group 1 and 2 hydroxide. Okay, why is that important? Okay, so it's important because strong acids and strong bases break up completely in water. So let's start with, let's say, HCl. HCl, and the proper word is ionizes, okay, breaks up into ions, in other words, ionizes completely in water. So when acids break up, okay, in this case it gives hydrogens always, and in this case it will give chloride ions, and then that H doesn't like being by itself, so it immediately grabs hold of the water and becomes hydronium ions, okay, and then the Cl is still there as well. Okay, so this is a strong acid, and it is also monoprotic. Now, what does that mean? Mono meaning one. It means that when my acid breaks up, first of all, it breaks up or ionizes completely. Okay, so if I tell you, for example, the concentration of the acid is 0.1 mole per decimeter cubed, then the concentration of the hydronium would also be 0.1 mole per decimeter cubed, and the concentration of the chloride would also be 0.1 because it's all a 1 to 1 to 1 ratio. Okay, monoprotic means that if you have one acid, for every acid molecule, I should say rather, it always gives off one hydronium ion. Now, remember what concentration is. It's mole over volume. So if I say this, let's say I have hypothetically 1 million, okay, particles of HCl, and I dissolve it in a liter of water, then when this breaks up, I will still have 1 million H's, because every million HCl's will break up and give me 1 million H's, and then also still 1 million chloride ions. So my concentration of my H will still be 1 million per liter, and my concentration of my chloride will still be 1 million per liter. So the concentration stays constant. Okay, that's crucial. With strong acids and bases, the concentration of your acid is equal to the concentration of your hydronium ions. If you have, for example, a diprotic, di meaning 2 acid, then if you take a look at this, first of all, this will break up and give me 2 hydrogen ions and then a sulfate ion. And I always think acids and bases is a tricky section because it's where everything comes together. You have to know, for example, your charge of your compound ions, your sulfates, your nitrates, things like that here as well. Okay, so my sulfate is here. Sorry, don't forget your charge there. Now, if I give you a concentration of the sulfuric acid as, let's say, 0.1 mole per decimeter cubed, could you predict the concentration of the hydronium ions? Well, this is a strong acid once again, so it breaks up completely in water, but it's also a diprotic strong acid. Di meaning two, which means that every one acid molecule gives me two hydrogens, which then grabs onto two waters and give me two hydronium ions. By the way, if you put a 2 there, you'll also put a 2 there, so they're not hard to balance. Okay, so that's important because if the concentration of your acid is 0.1 mole per decimeter cubed, then the concentration of your base would be 0.1 times 2 to get your concentration of your hydronium. Okay, and your sulfate would be 0.1 because there's a 1 in front here. Okay, but it's not really the sulfate we worry about for the most part, it's the hydronium ions we worry about. Let's talk about a base for a second. If you had a strong base, like in this case we have sodium hydroxide, which is a strong base. It's a group 1 or 2 hydroxide. Okay, what happens is that strong base will break up completely in water, okay, and it will give you sodium and hydroxide. Okay, so it is a strong base. And for bases, we don't say the word monoprotic, we say monobasic. Okay, which boils down to the same thing. For every one molecule of base, you'll give one molecule of hydroxide ions. So if I say the concentration of the sodium hydroxide is 0.1, then the concentration of the hydroxide is also 0.1 because it's strong and monobasic. If it had been a dibasic base, then it would be a 1 to 2 ratio with the hydroxide ions. Okay, so you are able to predict, this is what it boils down to, you are able to predict the concentration of the hydroxides or the hydroniums when it comes to strong acids and bases. But you also need to look at if the acid or base is monoprotic or monobasic or diprotic or triprotic to be able to figure out the concentration of the base. So for once you're allowed to use what I'm going to call a concentration ratio, which is not something we're normally allowed to do. We're usually allowed to do mole ratios according to these numbers, but because it's a strong acid or base, I know it breaks up completely, so I know the concentration will stay constant or be multiplied by 2 in the case of diprotic or dibasic acids and bases. Okay, why is that important? Okay, so they've given us this acid in this case, which is a weak acid. Okay, they've also given us the base. Okay, they've given us the volume of the base and the concentration of the base. And then they ask us the first question. When 0.1 mole per decimeter cubed of this carbonic acid is prepared, it's found that the concentration of the hydrogen carbonate ions to be only 0.012 mole per decimeter cubed. Okay, so what does that mean? So they are reminding us that the concentration of the acid is not equal to the concentration of the ions that form. So let's take this carbonic acid for a second and let's write that down so it makes more sense. So we have carbonic acid, which you can see is diprotic, but they're only making it break up and lose one hydrogen because we're forming HCO3. So the fact that it's diprotic isn't really important, okay, at the moment. And then that little H, so this will break up in 2 steps, but they're just saying, look, don't lose both hydrogens. Okay, we'll lose one hydrogen. Okay, so it's still a 1-to-1 ratio, even though it's diprotic, because they're probably going to do this in 2 steps. Okay, but we're only looking at the first step, I should rather say. Okay, so it's forming hydrogen carbonate ions, and it's a 1-to-1 ratio. Now, they have just said that the concentration of the acid was 0.1 mole per decimeter cubed, and yet the concentration of the hydrogen carbonate is 0.012 mole per decimeter cubed. So a lot smaller because this is not strong. So it doesn't break up completely, it doesn't ionize completely. So this concentration is a lot smaller than this concentration, okay? Which is why they had to give us the concentration. They couldn't ask us to predict it because it wasn't strong. And then they ask us to calculate the number of moles of hydronium ions. Okay, sorry, don't forget your charges like me. To calculate the concentration of the hydronium ions here, if you mix this, and they say at 25 degrees Celsius. Why is the temperature important? Because at the moment, not crucial, but later on in the question it becomes crucial because the ionization constant of water is 1 times 10 to the negative 14. And at higher temperatures, that value will change. Okay, so that's why it's important that they mention the temperature. You're not going to do anything with the temperature. You just need to be aware that that value is true at 25 degrees Celsius. Okay, so you can see from this balanced equation, this is a 1-to-1 ratio. So they gave us this, which means I can also say that the concentration of the hydronium is also 0.012. Okay, so they're not trying to trick us. Okay, so we can therefore say, let's write down the mole here. So for the first question, question 8.2, they've asked us what the mole is for the hydronium concentration, which is the same as for the hydrogen carbonate. So the concentration is the same. So I say concentration times volume, and I get 0.006 mole, which I'd rather put in scientific notation. Otherwise, I'm going to end up cutting off a value, rounding off too much, and I try to prevent that as much as possible. Okay, so we have the concentration of the hydronium ions in that beaker. Then the two beakers are added together. Before they're added together, they ask us to calculate the number of moles of hydroxide ions in beaker B. Okay, now that's not difficult. Let's just quickly remind ourselves that because sodium hydroxide is strong, okay, the concentration of the hydroxides will be equal to the concentration of the sodium hydroxide. Okay, so again, they're not trying to trick you. Okay, they want you to realize that because it's strong and monobasic, okay, it's a 1-to-1 ratio. So whatever the concentration is of the sodium hydroxide, it's the same for the hydroxide ions. So if I were you, I would just write that down to begin with. I would say, remember square brackets means concentration. I would say the concentration of the hydroxide, is equal to the sodium hydroxide. And that's why I'm allowed to sub in the sodium hydroxide concentration, okay, instead of the hydroxide, because I know they're equal. Okay, and I end up getting 0.1875, which I've rounded to 0.19 mole. Okay, I'm actually going to keep that whole value for my next calculation, which is going to ask you to work out the pH of the final solution. Okay, so the final question is to work out the pH of this solution. Now, before we work it out, let's just talk in general what we're really trying to do. Okay, so I'm going to take it back a step and pretend or give you a hypothetical situation. If I have a strong acid and a strong base, and I add them together in a beaker, okay, and I add the, quotes, correct amount of these two, in other words, a correct mole ratio, okay, so let's say I add 2 moles of this and 2 moles of this, I should form a salt and water, okay, and if I add 2 moles of each, they'll completely balance each other out, and my final product will be a salt, which is neutral, and water, which is neutral, and my pH would just be 7. And that would be a silly question to ask for 7 marks, okay? But if I say add 3 moles of the base instead of 2 moles, then my pH will not be 7 when these two things have reacted with each other. Because I have excess base and ultimately therefore excess hydroxide, what I'll form is salt and water and the extra hydroxide that comes from the extra base. And that will cause my pH to be above 7 when these two things have reacted with each other. Okay, so what I'm trying to say is that if your pH isn't 7, which, I mean, they wouldn't ask me a question like that for 7 marks if the pH was just 7. If the pH is not 7, it's because something is in excess in your reactants. And your job is to figure out what is in excess, first of all, how much is in excess, the concentration of the excess, and then the pH of that final solution. Okay, so this one is maybe a little more straightforward in the sense that they've given us a strong base and a weak acid, and they've asked us to work out the pH when these two have reacted with each other. Now, I'm going to assume that the base, there's going to be more hydroxides from the base because it's strong, okay, but that's not safe to assume, so let's do the calculations. So I've written down what they've given us here. They've given us we've worked out rather, the mole of the carbonic acid, and we worked out the mole of the sodium hydroxide. okay, which is ultimately the same as the mole for the hydronium and the mole for the hydroxides. Okay, then I'm going to, and I like doing any sort of mole ratio things in columns, so I know which belongs. Then I'm going to work out, and again, if you do this, just make sure to write little labels. Then I'm going to work out which one is an excess here. And I'm going to do that by saying what I was given, if I assume that this is correct, I'm going to do the ratio here. Okay, and it was a 1-to-1 ratio. They did give us a balanced reaction. Let's just double check that. Okay, the balanced reaction was a 1-to-1 ratio for the sodium hydroxide to the carbonic acid. Okay, so I'm going to take this and I'm going to say 0.1875 mole. Now, how I do mole ratio, I always divide by the one I'm with and times by the one I'm going to. So 0.1875 mole divided by 1 times by 1. If this had been a 2, I would have divided by 2 and times by 1. If this had been a 3, I would have divided by 1 and times by 3. So always divide by the one I'm with, times by the one I'm going to. And I get 0.1875 mole of the carbonic acid. Okay, then if I assume that this one is correct, okay, and I do mole ratio and I say 0.006 mole, okay, and I'm dividing by the one I'm with, times by the one I'm going to, so divide by 1 times by 1, which gives me 0.006 mole of hydroxide or sodium hydroxide. Then let's check within the column. Please don't ever compare across columns. You were given 0.006 mole of carbonic acid, but you need 0.1875 mole. You have way less than you need, which makes this the limiting reagent. Okay, which means that the sodium hydroxide is in excess. Okay, so as we go, let's write down little steps. Let's write down little steps we're taking to figure out what the pH of the final solution is. So step 1, determine which substance is in excess. Okay, now your final pH of your final solution will be there and won't be 7, let's say, because of the excess acid or base that's floating in the solution. So people always ask, like, should you not take the pH of the final solution, let's say it's water and a neutral salt, and subtract the excess or anything like that? And the answer is no. Your excess, your pH of your final solution is purely there because of the excess, either hydroxides or hydroniums. That's why the pH isn't neutral. Okay, so we're trying to figure out what's in excess, how much is in excess, and then basically working out the pH of the excess. So step 2 will be determine how much is in excess. Okay, I'm going to be specific, determine how many moles in excess. And since pH has to do with concentration, your step 3 is determine the concentration of the excess. And this is usually where people make their first mistake, so we're going to look very closely at that. Okay, so let's come back to that in a second. So let's now do exactly that. Let's work out so this was step 1, then let's do step 2. We're going to work out how much is in excess, okay, by saying the given minus the needed. Okay, and this is just a little formula for yourself if it helps you understand. So 0.1875 mole minus 0.006 mole, and that gives me 0.1815 mole, and I'm trying not to round off. As a rule, I generally say keep 4 decimal places until your final answer, so that we're not rounding off again and again in multiple steps. Then we're going to find the concentration of the excess. Okay, I'm just going to write here the excess base so I don't lose track of what's happening. Okay, so I take the excess mole, again, I'm going to write a little subscript here. So the excess mole is 0.1815. Now this is what, like I said, where people usually make their first mistake. What volume do you think we're going to say is here? What volume is this excess floating in? Well, you have to remember that you've now added the acid and the base together, and that excess is floating in the total volume. Okay, so it's the 0.5 decimeter cubed plus the 0.75 decimeters cubed. It's the total volume, and that's usually where people make their first mistake, and they just use the volume of the base to work out that concentration, and they forget that they've now added these two together, and the entire volume is now together, and the excess is floating in that entire volume. Okay, then, and this is usually something people forget as well. Ultimately, you're looking for the pH, and pH has to do with the concentration of the hydronium ions. Okay, so I need to, before I can find that, I need to find how much or how many hydroxide ions are in excess, or the concentration of the hydroxide ions in excess. And this is straightforward, and this is why oftentimes the memos won't even show this, because this is a monoprotic acid, or base rather, monobasic rather than monoprotic. Okay, the concentrations will be equal. So the concentration will also be 0.1452. Okay, I don't like not showing this step, because if it's dibasic, you'll have to times this by 2 to get the hydroxide concentration. Okay, so don't forget that step. Okay, then my next step is to try and take the hydroxide concentration and to figure out the hydronium. And the formula that puts these two together is this hydronium concentration multiplied by hydroxide concentration gives me that ionization constant of 1 times 10 to the negative 14. And that's why they had to tell us the temperature. Because remember, this value is only true at 25 degrees Celsius. So I know in any solution at 25 degrees Celsius, the maximum product of ions that can dissolve in that solution is 1 times 10 to the negative 14. Okay, and now I have my hydroxide concentration, which is 0.14, not my base's concentration, my hydroxide, which is so important why I did that step. Okay, then you divide both sides by 0.1452, and then you get the hydronium concentration to be 6.8871. Again, keep 4 decimals, mole per decimeter cubed. Okay, and then finally I can plug that into my pH calculation. Okay, and I can say pH is equal to negative log of my hydronium concentration, which is negative log of 6.8871 times 10 to the negative 14, which gives me a final answer of 13.16. So let's just finish our little steps here. Okay, so step 4, determine the either hydroxide or hydronium, depending on what it is in excess, concentration. Okay, square brackets means concentration. Let's just add here, determine the excess concentration of that. Okay, and you might think that step is silly or unnecessary, but remember, if the acid or base isn't monoprotic or monobasic, then the concentration isn't 1 to 1. Then we have to double it or triple it. Then for step 5, we then took that excess hydroxide and we determined in this case, in another example, you might be working out the hydroxides at this point, okay, using this formula. Okay, and although this is steps to solve a question like this, they could obviously ask the question slightly differently, and then we have to approach the question differently. But if you get something like this and you've given enough information to work out the moles of both the acid or the base, then you're probably going to have a very similar sort of scenario like this, where why would they give you the moles for both? Surely it's because something is in excess, and we have to try and figure out which one is in excess, and then work out that pH of the excess. And then finally we determined the pH, okay, using pH is equal to negative log of the hydronium ion concentration. Okay, so quite a daunting question. Okay, but this is how you would approach it when you have an acid and a base added together and you have to figure out the pH of the final solution.